All right, we'll go ahead and get started. It's 10 o'clock. Thank you, everybody, for joining us to another long coffee break. My name's Aaron Morris. I'm sales engineer with Long out of the Colorado Springs office. Today, we're going to be talking about noise control design for high-performance schools. We'll be looking at the CHIPS certification requirements, but really some of the stuff we're going to be covering would apply to any building, any application that has sound sensitive requirements. A couple of terms to be familiar with: octave frequency bands, basically the full audio spectrum divided up into 10 octave bands. We typically use the 63 hertz through 8,000 hertz. And something to know, kind of each of those octave bands is actually comprised of a range of frequencies. So like the 1,000 hertz or 1 kilohertz octave band is really going to be anything measured between like about 770 hertz up to 1,400 hertz. Anything recorded in those frequencies would fall into that 1 kilohertz octave band. Difference between sound power and sound pressure. Sound power is going to be the total sound energy that's generated by the source. Sound pressure is going to be, as you move away from that source, you're going to have reduced sound pressure. And sound pressure is actually what they're going to be measuring with the sound level meters, measuring the changes in atmospheric pressure due to those sound waves passing through. And then some abbreviations. dB for decibel is common unit of measure for sound pressure. dBA refers to kind of those 8 octave bands all averaged together on a weighted scale. So it's the A weighted scale, which is intended to, kind of focus on the octave bands that are perceived best by humans. LAEQ is what you're going to see in the CHIPS certification, the scorecard. So it's really the dBA, the A-weighted scale, but measured over a period of time. So it's the equivalent continuous sound level where it's the total sound energy throughout that fluctuating noise levels measured over a period of time. NC stands for noise criteria, which is a common way of referring to sound requirements in a room. The NC curves have also been developed to focus on the octave bands that are best perceived by us. And kind of the way that works is if any octave band measured value goes above that curve, you don't meet that NC level. STC, sound transmission class, it's in the CHIPS standard, but more to do with kind of structural architectural components, how they construct their walls, things like that, with a high transmission loss construction so that you don't get sound transmitting from one classroom to the next. If you have HVAC, ductwork passing through a STC rated wall, you may need to look at it to see if you're going to need attenuation to maintain that STC rating. But typically we haven't seen that in classrooms. That's more for, more sound sensitive applications like SCIF rooms. So looking at the dB scale, just a visual for you, kind of showing, starting at the bottom there, it like a dB of 30, is a whisper, right? So really quiet. Up to, then 85 in the middle, where it could potentially start being harmful to your hearing, all the way up to, the 140 equivalent to, gunshots, sirens, fireworks, right? The CHIPS prerequisite requirement is a dBA of 45. So you would have to design for that target in order to meet the CHIPS certification. If you want to pick up some enhanced points, you're going to be looking at dBA of 40 or 35. So you can see we're really targeting, way down on the lower end of that scale. So really, very, very quiet in the space. So when you're now we can get started looking at what you need to consider when looking at a design. You're going to have a piece of equipment that's going to be your source of your noise, and then depending where that piece of equipment is located uh, next to your space, you'll need to consider all four of these sound transmission paths. So you're going to have ductborne noise where the sound is traveling, through that ductwork. You're going to have the breakout noise where the sound breaks out through that ductwork, and goes down straight into the space or to the sides. Radiated noise that's coming directly from the equipment, radiating out in all directions. So depending, again, if this is a rooftop piece of equipment, like you see in this example, you're worried about the noise radiating down into the space. If it's a mechanical room, you might be concerned about it radiating through the walls, that sort of thing. And then finally, vibration transmission, where the vibration from the equipment could potentially be transmitted through the structural components of the building and causing noise or vibration complaints in the space. So to start, you're going to need to know what your requirement is. So at the top here, we're seeing, a little snippet from the CHIP scorecard. Um, you're going to have the 45 dBA prerequisite. So if you're trying to get certification, you're going to have to design to that 45 dBA in your classrooms. And then if you're trying to pick up extra points, you can see the 40 or 35 dBA to pick up either 1 or 3 points. Now, to know if you're going to be able to do that, you'll need to know the sound power from the equipment you're going to be using as your basis of design. So at the bottom, there's a little snip from a Daikin rooftop unit selection, where you can see we're looking at sound power in dB, and we have the 8 octave bands, and we're showing the inlet or return air duct connection sound power, the discharge or the supply air duct connection sound power, and then the radiated sound power that would be coming from the equipment. So if we know our sound power levels from our basis of design equipment, and we know our goal that we're trying to achieve, the other piece we would need would be a floor plan showing where that equipment is located relative to the space and the duct path that we're designing to get from that equipment to the space. Something else to consider here: if sound is important to your project, you want to make sure that you get your sound levels for your equipment scheduled. So it's on the drawings, kind of what that basis of design is. So if you're allowing alternate equipment, they can make sure that they meet that sound requirement, or compensate with additional attenuation if needed to get the space to the sound requirement of that 45 or 35 dBA. So if we know our sound power level for our equipment and the requirement for the space, and we know our duct path, then we can send that information to Vibra-Acoustics, who can help us with a acoustical analysis that'll look something like this. Now we can start off with a baseline analysis just to show, with the top line showing the rooftop unit sound power levels, and then the distance it travels through the ductwork, different fittings, different branches that it's going to travel through before it gets to the classroom. We can calculate insertion loss values and show where we would be if we do not add sound treatment. And in this case, we were going to be well above the target of the NC30 contour line. So we added this silencer number 6 in this case, which was a supplier silencer that we installed. And then in this calculation, they're showing the insertion loss of the silencer. And on the bottom line, they're showing that, with the each octave band, what the resulting sound pressure is going to be, and the resulting NC26, which is below the NC30 target. Another way to visualize that, I've plotted it onto NC curves here using a tool from Kruger's website. It's a free download, little noise calculator. You can plug in. It gives you, spots to plug in up to 4 different runs. You plug in each octave band from the 125 hertz up to the 4,000 hertz. And then it plots it onto the NC curve and calculates the NC level and the dBA level. So handy little tool. In this case, we plotted the sound power straight from the rooftop unit in green, which is clearly, way too loud for the NC30. And then the blue would be if we did not use our silencer. It just, in the short amount of ductwork we had to get to this space, still going to be way too loud. So then in red, we plotted it with the Vibroacoustics sound attenuator. And you can see that each octave band comes in below that NC30 contour line, meeting the requirement for this project. And you can see in the final sound pressure here, we resulted in the NC30 and we had a dBA of 31. We're doing this using sound attenuators, which can come in all sorts of shapes and sizes here. Round, rectangular elbow, or really, custom attenuators in transitional, T-shape, whatever you need for your application. You can reach out and we can help work with Vibroacoustics to design an attenuator to fit your space. In this case, we were using a rectangular elbow silencer. Some benefits of using an elbow. One, you can see that we needed a lot of attenuation in this case. So our center line length is 144 inches. So if this were a straight attenuator, it would take up 12 feet of space, but by using it as an elbow, we can divide that between the 2 legs of the elbow. And then the air pressure drop of this elbow comes in less than a SMACNA 90-degree elbow plus a 12-foot straight silencer would have. So, it's a better option for your air pressure drop. In the submittal here, you can see we'll provide the air pressure drop at the design CFM, and then the insertion loss for each octave band will show the number of dBs that'll be reduced by using the silencer. The other thing to note here is in the construction of this silencer, we're using HTL casing, which is a high transmission loss casing. So the sound won't travel through that sheet metal. So it addresses that breakout noise path as well. So with this silencer, we can cover both the ductborne noise and the breakout noise. So if we go back to those 4 transmission paths, we can see we've dealt with the ductborne noise and the breakout noise, which leaves us with the radiated and the vibration, right? So a couple ways you can mitigate those noise paths would be to move the equipment further from your space. That'll help with the radiated noise. You could move it out so it's over the corridor, for instance. There's some drawbacks because you might have additional ductwork, which comes at a cost, additional pressure drop, but that can be a good way to deal with the radiated noise. Another good way to deal with it would be a concrete equipment pad. If you can do that, then the mass of the concrete will do a good job dealing with that radiated noise and absorbing some of that vibration. If those are not options for you, then we can work with Vibroacoustics to design a noise control curve that will really deal with all 4 sound transmission paths in one piece of equipment here. So you can see we've got the built-in sound attenuators, which deal with the ductborne noise and the breakout noise. We've got a noise control barrier, which is rated sound media, so we can design it to meet the requirements for the project. And then finally, we have a spring isolated curb rail to deal with that vibration transmission going into the building. So really, whatever your application is, we can do a baseline analysis that will let you know if treatment is needed. And then if it's determined that treatment is needed, we can help find solutions for, all of those possible noise paths to get the space level sound, the sound level in the space, down where it's required for your project. So in summary, if you have a sound sensitive application, please reach out to your Long sales engineer. They can help get the information needed to get a design from Vibroacoustics to meet the sound requirement for your project. Thank you for joining us. Hope you'll also tune in next week. We're going to have Jeff Rodell introducing a new line for us, which is Strobic Air lab fans. And then finally, today's prizes are a $100 Macy's gift card, a mini projector with Wi-Fi Bluetooth capability, and a Assume I'm Right to Save Time desk sign. Thank you, everybody, for joining us today. Have a good day.